2015 was a pretty exciting time in the Miller household because my wife was pregnant with a third child. And to that point, we'd had two boys. So what people were discussing is, well, what's the third child going to be? And secretly, and I'll tell you this secretly, girls, that my wife did want a girl. Right? So some people, would say, oh, like, two boys already, so, probably going to be a girl this time. And to those people, I unfortunately had to take the mathematical approach to say, actually, there's just a 1 in 2 chance, a 1 in 2 chance. So I kind of did buy into the discussion. Oh, I wonder what it's going to be. But the reality was mentally, I just knew it's a 1 in 2 chance. It's a 1 in 2 chance. All right, so here is what I would explain mathematically to anyone who is that way inclined that wanted to further engage in this discussion. That when you have a child, it's either going to be a boy or a girl. And the chance of getting a boy is 1 in 2, girl 1 in 2. Now let's have a look at what happens after you have a boy. If you decide to have a second child, you can either have a boy or a girl. In which case, the chances are still 1 in 2 and 1 in 2. Now notice something interesting here, girls, is that when you have a boy first, have a look at the chance here of getting a boy second. Wow, it's still 1 in 2. That there's nothing that changes on this second branch here if the first child is a boy, all right? So what we can say here is that the probability of a boy, given that the first child was a boy, it's still 1 in 2, okay? So if you told me, like if I'm talking to someone and they say they're going to have a second child and they speculate on the sex, there's no point asking them what they've previously had. No point asking them. It might be an interesting discussion point, or what have you had so far? But the reality is it does not matter what their previous children and the sex of those children have been. There's still a 1 in 2 chance. And so, in fact, the probability of probability of a boy given a boy has happened as 1 in 2 is exactly the same as the probability of getting a boy. Okay, it's 1 in 2. So that's going to be an interesting thing because that's part of a formula that we're going to discuss later on. So I know that that's a little bit mathematical, girls, and it takes away some of the kind of excitement, ooh, having a kid and all that sort of stuff. But that's mathematically the way this works, that these are independent of each other. All right, now I've just placed on the screen an image of the spins of a roulette wheel. Now, a roulette wheel at a casino is that wheel that you basically put a ball in and spin, and one of the basic bets on a roulette wheel is that you can get bet on red or you can bet on black coming up. Now, have a look at this result list here, and what you can see is the numbers, okay? But you can also see what color came up, okay? And so we've got a 27 red, 29 black, 17 black, 24 black, 33. Obviously, they couldn't put it in black because you couldn't see it, etc., etc. And you notice that this run here of long, like a lot of black numbers here. So I just want to ask you guys what you would do if this run came up, that it was 29, 17, 24, 33, 22, 29, 20, 31, 4. If I gave you $100 at this point and I said, what would you put your money on, red or black? All right. What would you say? Have a think about your answer and then unpause this video. I'll pause the video, have a think, and then unpause it. Well, if you've unpaused it, what I'm hoping you said was, it doesn't matter. Okay, it doesn't matter what the previous results have been, that I'll bet on like red because I like red. I'll bet on black because I feel like it. I'll bet on red because I just flipped a coin and I said heads was red and tails was black and heads came up or something. So the real answer to that question is, girls, that if you want to know why it doesn't matter, it's the next spin of the roulette wheel doesn't depend on the results of the previous wheel. And casinos who put this stuff up actually are putting that up to play on what we call the Gamblers Fallacy. Okay, the Gamblers Fallacy, or betting on the hot hand. All right, and so what you see at casinos, you'll see people or players gather around this table as if something amazing is about to happen. They think it's about to pay off. Casinos love this because casinos think that, players will go, oh, like, yeah, and they'll drop more money on this table. Whereas the reality is at this point here, a red or a black has got equal chance of coming up. But again, people will bet money on this table and more money on this table than other tables because they think they've got more of a chance of winning. So casinos love this. In fact, if this sign wasn't there, it shouldn't change anything. Okay, you would bet on this table as if you would any others. But can I just clarify that statement about betting on this table is that in fact, the more you gamble at the casino, I'll guarantee you one thing: you're going to lose. That's the absolute guarantee about gambling and working at the casino is that if you ever have won even a little bit of money, a dollar, whatever it is at a casino, do not bet again. Never ever bet again, because the longer you play at a casino, statistically, the more chance you've got of losing. Okay, so go spend your money on something constructive rather than dropping your money at casinos, because all you'll do at that place is make someone else a lot of money, not yourself. That's what I can guarantee. All right, back to the notes. So let's have a look at a couple of other events here. So we've got a tree diagram shows 2 selections of marble from a bag of 2 aqua. So I usually go aqua, 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 and blue, blue, blue to represent the marbles. And you notice here that with replacement, what happens is that let's just take this event here, A given B. What's the probability of getting an A given B has happened? All right, now you notice there that it's 2 in 5. All right, and you notice that that's the same as the probability of getting an A in the first place. And that means that these events are independent. So in the first tree, we can see that if the probability of A given B is the same as the probability of A, we say that these are independent. And of course that would be the case. If this event was running in class and I picked a marble out and chucked it back in and I'm like, ooh, what am I going to get next, girls, given that the first one was an A? You'd be like, I don't care, Mr. Miller, what came up first. I don't give a stuff what came up first, okay? Because he chucked it back in the bag, everything goes back to square one. Now let's have a look at this case here. This is without replacement, okay? And let's look at the probability of A given B. So B has happened, and the probability of A is 1 in 2, all right? Now that is not the same as the probability of A, which is 2 in 5. So now if I ran this experiment and I said, hey girls, I'm not going to replace it. Do you want to know what came up first? You'd be like, yes, definitely, because what came up first is going to dictate or affect the chances of whatever's going to come up second. So in the second tree diagram, we say that the probability of A given B is not the same as the probability of A. So these events are not independent, okay? So for independent events, we know that the probability of A given B is the same as the probability of A. And we also know from the conditional probability formula that the probability of A given B is equal to the probability of A intersect B over the probability of B. Now, what we can do also here at this point, girls, is write or rearrange the formula. So we can actually use this formula here, probability of A given B. So what I can do is put this part here into that part there. All right, so I simply replace the A given B with probability of A intersect B over probability of B. All right, so I'm just going to do that next to here so you see how the formula comes out. So instead of writing probability of A given B, I'm going to write the probability of A intersect B over the probability of B equals this thing here, the probability of A. And what I'm going to do is multiply both sides by the probability of B. So for independent events, what will happen is the probability of A intersect B will be the same as the probability of A times the probability of B. All right, so that's another formula there, okay? So that one there for independent events will give you that formula and will give you that formula there. So that's just a way or a good method to check for independence. All right, so if 2 events are independent or if the outcome of one does not change the other, then we know that this will be the case. The probability of A given B is the same as the probability of A, and also that this will be true. All right, so let's have a look at an example. When a card is picked at random from a standard deck of cards, 4 suits, no jokers, are the events K, a king is picked, and D, a diamond is picked, independent? Don't know. All right, so let's check it out. All right, so what we're going to say here is that the probability, so we're going to have the event king and the event diamond, okay? Now, in the middle is the king of diamonds, king and diamond. The amount of diamonds is 12. The amount of kings is 4, with 3 left, with 1 being the king of diamond. And that leaves us with, how many? Like that's 13, 16, 52 take away 16, 42, 36. 36 being neither king nor diamonds. All right, so what are we going to do? Well, we can look at independent events by saying the probability of king given, not B, king given that a diamond is picked is equal to the probability of a king. That's what I want to know. So is this true? Is the probability of king given a diamond is picked the same as the probability of getting a king? Let's have a look. So diamond has been, that event has been selected, right? So now we've shrunk the sample space and all of this stuff outside it doesn't matter. So what are the chances of getting a king? Well, we've got 1 in 13, okay? Right, now, what are my chances of getting a king? Well, there's 4 kings in a deck of 52 cards. Okay, that's the probability of getting a king. And it just so happens that 4 in 52 is 1 in 13. Okay, so therefore, independent. All right, so yes, they are independent events. So if a diamond is picked, the chance of getting a king, you wouldn't be like, ooh, was a diamond picked, was it? Like, ooh, that's going to be interesting. Now that changes anything. The fact that a diamond is picked does not matter. So if I tried to run this card game with you and I said, all right, girls, what are my chances of getting a king? Given that, and I look at the card and I go, ooh, it's a diamond, girls. You should be like, that doesn't matter, Mr. Miller. I don't care what it was. Okay. Now, another way to prove this is to use the other formula, which is probability of king and diamond equals the probability of king times the probability of diamond. Okay, so we can use this particular formula. So king and diamond is 1 in 52. Probability, now why did I use A again? So that's king. So we saw that the probability of getting a king is 1 in 13. And the probability of getting a diamond is, what is it? The probability of a diamond is 13 in 52 or 1 in 4. Okay, so I'm just going to get rid of the 13 in 52 and write it as 1 in 4. Now 1 in 52 equals 1, 13 fours. It just so happens it's 52, therefore independent. Right, so you can use the check there to confirm independence or confirm that the events are not independent. All right, this next case or this next question is a particularly interesting one. I'm going to go back to this statement at the top here and get straight into the example. Suppose we roll the dice twice and define the following events. First roll shows a 4. Well, what are my chances of getting a 4 on the first roll? So the probability of A is going to be, let's have a look at which one this is. That's this one here, 4, 4, 4, 4. That's 6 out of 36, or it's a 1 in 6 chance. Second roll shows a 4. Well, that's this case here, of which there's 6 potential options for that, or there's a 1 in 6 chance, 6 in 36, 1 in 6. Some of the numbers being at least 10. Well, we've got 1, 2, 3, 4, 5, 6. 6 in 36, 1 in 6 chance. At least 9. He's going to add 1, 2, 3, 4 more events. That's going to be probability D. That's going to be 10 in 36, which is 5 in 18. Right, are A and B independent events? And let's have a look. A is first roll shows a 4, B is second roll shows a 4. I'm going to say yes, absolutely, right? Absolutely they are independent events because, again, in a dice game, if I tell you I roll the dice and then I roll the dice again and I say, hey, what are the chances of getting a 4 given that the first roll is a 4? You should say, well, yeah, 1 in 6, Mr. Miller. Like, what are we talking about? So let's just confirm that these are independent events. There's two ways of doing it. So I'm going to use the independent events formula. This is just my preferred one. Probability of A times the probability of B. All right, so what are the chances? So A and B. So that's first roll shows a 4 and second roll shows a 4. That's 4, 4. That's this event here. That's a 1 in 36 chance. What's the probability of A? 1 in 6. Probability of B? 1 in 6. 1 in 36 equals 1 in 36. Therefore, as we suspected, the events are independent. What about A and C? Right, so first roll shows a 4. Sum of the numbers showing is at least 10. Okay, so if that was the game here, girls, and I said, all right, look, we're looking for a number that's at least 10. Would you be interested in knowing what the first roll is? Okay, would you be interested in me telling you whether if the first roll was a 4? And you'd probably go, yeah, I'd be interested. Okay, and therefore, if I said to you, hey, what do you think? Are these events dependent or independent? You'd probably say, no, that depends. The chance of getting a 10 does depend on what that first roll is. Let's find out. Right, so probability A and C. Sum of the numbers showing is at least 10. First roll is a 4. Probability of A and C equals the probability of A times the probability of C. Okay, first roll is a 4. Sum is at least 10. First roll is a 4 is this event here. Sum is at least 10. That's the only one that matches it. So this is a 1 in 36 chance. That's the 4,6 option. All right, the probability of A, first roll shows a 4. That's 1 in 6 times the probability of C. Some of the numbers showing is at least 10, 1 in 6. And notice something really interesting about this case, girls, is that the events are independent. So if we're trying to make at least 10, the information first roll is a 4 should not matter. Well, not should not matter, it does not matter. Okay. All right, what about A and D? Some of the numbers showing is at least 9, and first roll shows a 4. Okay, so probability of A and D is equal to the probability of A times the probability of D. A and D, first roll is a 4, and sum is 9. Right, so I'm going to go over here and note first roll is a 4, this one. So we've got 1, 2. 2 in 36 equals 1 in 18 equals the probability of A, which is 1 over 6, times the probability of D, which is 5 in 18. All right, so we got 1 in 18 is equal to, let's multiply it out, 5 over 6 times 18, I don't even know what that is, 8, 4, 1, 6, 6, 10. All right, and what is painfully evident is that an 18th is not the same as 5 over 108. I hope you know that they're different. So what we're going to do is slash that to say that these are not equal to each other. So therefore, that is the same as that, which is not the same as this side here. What's the confirmation here? These events are not independent. Okay, so that's the conclusion that we can make. Okay, that the first roll being a 4 does affect this event here, D. The sum of the numbers showing is at least 9. Now, the moral of the story is sometimes you'll think that events are independent or dependent, like this one here. My gut feeling always says, and even still, if you ask me, are these events independent, Mr. Miller? I would go, do the test. Do the test, okay, and you can't go wrong. So for any of these events that you're unsure about, or if it asks you to show that events are independent, you must complete the test for independence. All right, so on to exercise 8G and commence your revision, Chapter 8 review.